Good afternoon and welcome to our IAC seminars series. It's really a pleasure for me to introduce the speaker today, Professor Francesco Solombrino. Full professor in mathematical analysis at the Department of Mathematics and Applications Renato Cacciopoli of the University of Naples Federico II. He has been principal investigator of several research projects, supervisor and bachelor, master and PhD thesis, organizer and invited speaker of many relevant national and international events. He is author of a significant number of scientific papers with very high national and international impact. He has several research interests, among them in particular those related to variational methods in continuum mechanics, limit analysis and optimal control of kinetic models of collective motion with stochastic terms. Well, now I leave the floor to Francesco. I thank him for accepting our invitation, and I recall the title of his talk, Fractional Approach to Strain Gradient Plasticity Beyond the Chord Radius of Discrete Dislocation. Please, Francesco, and thank you again.
Thank you, Claudia, for the introduction, and thanks to all the organizers for inviting me to deliver this talk. It's a special pleasure, actually, also because of a curious fact. For a while, I lived in this street, Via Pietro Castellino, for years, but I never was to IAC in Naples, so better late than never. So I'm pleased to be here to present this paper. This is a joint work with Stefano Almi of the University of Naples, Maicol Caponi now in L'Aquila, and Manuel Friedrich, who is professor in Erlangen in Germany. And what we are going to present is some, for sure, variational calculus, for sure, continuum mechanics, and this some asymptotic approach to deduce some toy models for strain gradient plasticity from fractional elasticity. I will clarify what I mean by that and what the advantage with respect to the traditional approaches are. Let me start with a warning. There will be some technical aspects. I may want to highlight some of them, but nevertheless, I will try to stay as general as possible to illustrate the ideas instead of the technical aspects. And the good point is that along this journey, I will have to recall some basic results. What are the models we are going to approach? What was the traditional way, the nowadays established way, which is come out in the last 20 years to deduce these theories, and what our contribution was. So let us now check if everything works. So the beginning of the story is we want to derive some effective models for plasticity. And as you may know, plasticity is a phenomenon that may happen in elastic materials and the onset of yielding. So you have an elastic material which is submitted to a certain load, and when this load exceeds a certain threshold, the material behaves no more elastically. So some defect appears, a permanent change in shape is now tied to the material. So there is an irreversible deformation. This is what you see from a macroscopic point of view, while it is very well known from the microscopic point of view that what happens is actually the effect of the presence of these defects, these small defects in the crystalline structure of the material, which are called dislocations. So you have to think that an elastic material has some crystalline structure, and at a certain point, it is a load is applied to the material, and a loop that in the original configuration was closing is now no more a closed one. So the lattice was deformed, and now if you go twice to the left, then twice down, twice to the right, and twice up, you do not close the loop of your atomic bonds, but instead you have seen the formation of a small defect, which is an integer combination of the lattice direction, and this defect is indicated with this notation B, and is called the Burger's vector, which represents the magnitude and the direction of the lattice distortion. So this is what you see from a microscopic point of view. And how do you describe, from a variational perspective, the formation of a plastic deformation? most well-known models date back to these works by Fleck and Hutchinson or Gertin, and are so-called strain gradient theories. So what happens? You imagine this is a microscopic description. So now we are back to the usual world, and we have a deformation U, a deformation field applied to the reference configuration of the material. For simplicity, in all of this talk, we will think of planar configurations and of planar deformations. And the deformation gradient, nabla U, is decomposed into two parts, an elastic part and a plastic one. And this decomposition is not determined a priori, it's the result of an energy competition between two kinds of energies. An elastic one, the simplest one you may think of, also maybe physically not so well justified, is a linearly elastic one, so a quadratic energy on the elastic strain beta E, and there is instead a plastic energy, pi, acting on the so-called nice dislocation density tensor, which is the curl of beta P, of the plastic part of the deformation gradient. And it is known that this plastic energy must not be of quadratic type, instead must have linear growth, must be one homogeneous in its variable, and what the materials does under a certain load is the result of this competition. So if possible, it prefers to be elastic, but if the elastic energy has become too big, then an elastic collapse appears and the plastic deformation is created. And one is not to be surprised that indeed it is postulated that the plastic deformation is depending on the curl of the strain tensor if one thinks of our microscopic interpretation. So in some sense, the formation of a defect was related to a circulation condition. Some loop did not close. Some line integral was not anymore zero, but instead was producing a positive result. And this is an integral condition that in differential calculus may be reformulated as a curl condition. But instead, indeed, this derivation was mainly macroscopic. So these models were deduced out of experiments, did not refer to the microscopic world, and so the link was missing for a while between these two theories, the microscopic one and the macroscopic one. And also there has been a certain effort in recent years to derive this macroscopic description as the variational limit of this microscopic one. By variational limit, I usually mean the characterization by gamma convergence, for those who know what gamma convergence is. For those who don't, they simply have to think that we have a sequence of variational problems on a lattice scale. This lattice scale is vanishing, so you have a sequence of variational problems, and you want a property that ensures you that minimizers of the original problems are converging to minimizers of the limit problem. And this you call recovering an effective energy, because instead of having a sequence of problems formulated on a microscopic scale, you only have one, which is the limit one, and you use that for doing your computation, your simulations, whatever you want to do. This is what I will mean in all of this talk by variational convergence, and for those who know, there is gamma convergence behind. But first of all, how is the model formulated? So usually you have a model which is intermediate among the two scales. So in some sense you have a macroscopic energy, so you have strain tensors, but you are remembering that there is some discrete dislocation structure. And so you have an elastic energy on a strain tensor which has to be coupled with this formation of dislocation. And as I told you before, the natural way of formulating this problem is via a differential constraint. So around a certain point in your configuration, dislocation cores are formed, and what is the mathematical form they take? There is a curl condition. So beta is not a gradient anymore, so curl beta is different from zero, but instead it is equal to a Dirac delta, accounting for the formation of a dislocation, and there is a magnitude psi, which is the Burgers vector. And usually it is postulated that this Burgers vector belongs to a finite set, which is reminiscent of the lattice direction, but you may think that a finite set is fixed and that you have this condition. The only point is that you cannot formulate the problem, the discrete problem in this way for a mathematical reason, because there is no configuration satisfying the differential constraint of having the curl being equal to a delta, which belongs to the Hilbert space L2, and so as finite, finite elastic energy. And this is easy to see for people who are acquainted with the theory of distributions and so-called space, because if you postulate that such an energy, I mean the elastic energy, which I'm showing here, is kept finite, this means that your strain beta is square integrable, belongs to the space L2. And then its curl, which is a derivative, goes in the Sobolev scala once back. So you are not more in L2, you are in the negative Sobolev space H-1. But unfortunately, your curve must be equal to a multiple of the Dirac delta. And when you are in dimension 2, it is well known that the Dirac delta does not belong to that space. So in some sense, if you want to say, I have a variational problem where my energy configurations minimize an elastic energy, remembering of elasticity, and have a differential constraint reminiscent of dislocation, the problem with this variational modeling is that there is no competitor satisfying both conditions, and so such a model is false. So what was the idea which has been introduced in the mathematical literature during this during the last 20 years? It is a very natural one. So you are going to accumulate an infinite amount of energy close to your dislocation core, cut it out. So introduce a so-called core radius. So instead of identifying a dislocation with a Dirac delta, you try a soft approximation of this constraint. So you postulate that at some positions in your reference configuration, some holes are formed, which have width epsilon, a very small one which you want to let be vanishing in the limit clear. But for the moment, let's stay with fixed epsilon. So outside of this so-called dislocation cores, which are very small, there can be a lot of them, but each of them is very small, the energy is the elastic one. If you want, the linear elastic, but there are also nonlinear possibilities which are probably more interesting from the point of view of the applications. But clearly you have to reformulate your differential constraint. You cannot say that now the curl of beta is equal to a multiple of a Dirac delta, since you cut out the region where the curl is concentrating. And so you reformulate according to Stokes' theorem. So you say that outside of dislocation cores, your curl must be 0, as it must be. And then you have a line integral, so the circulation of beta on the boundary of these small balls you cut out must be equal to your Burger's vector xi. So to one of the possible, because you have many possible competitors, to one of your possible Burger's vector xi. So this approach is called the so-called core radius approach, and I think there is no need for further explanation why this name was given. And the natural idea was, so let's suppose we have an elastic energy with these constraints. I will show you in one slide what we exactly mean by this, and we let the parameter epsilon go to 0. What happens, what one expects is that a plastic energy will appear, and that you can also characterize what is the energy associated to this phenomenon. So now there is a little bit of mathematics. So you can clearly have more than one dislocation. And so your dislocation density is not only made of one Dirac delta, but is a possible combination of Dirac deltas. The weights of these deltas are the Burger's vector, which are admissible for your model. It is not at all prescribed where the dislocations sit. They can be at each point of your reference configuration, so they can also move, but for the moment, we only have a stationary problem. There is no evolution in what I'm going to present. And there is a maybe very number of them, which we indicate by M. And the condition is that you cut out these M holes, you have your circulation conditions, so there is a compatibility between mu, the dislocation measure, and the strain beta, which is admissible, And so the energy is formulated in terms of two variables. One variable, beta, the elastic strain, which is responsible for the energy, and one dislocation density, mu, which appears out of your constraint, which is no more a differential one, but instead is an integral one. And so you have a model in two variables, and what you expect is that when the parameter epsilon goes to 0, and possibly the number of dislocation goes accordingly to plus infinity, this measure mu can also create some diffuse part out of homogenization, and that you are going to get a new model on beta and mu, which has not only the elastic part, but also the plastic part. And clearly, for doing that, you need some scaling of the energy. So to see something significant, you have to divide the energy to some factor which accounts for the unit energy spent for a dislocation. And this is easily calculated. So if you postulate that you only have one, an easy computation, actually, you can solve the equation curl beta equal to the Dirac delta multiplied by something. You can find the minimal solution for this problem with respect to the energy. You calculate how much energy this is concentrating around a dislocation core, and you discover that, as you may expect because of my previous discussion, this energy is going to plus infinity when epsilon is going to 0, and you exactly also know the order of this energy. It is of logarithmic order. So each dislocation is costing you logarithms of epsilon energy. If you have m of them, the energy spent superpose. And as I told you, a natural concept, if you want to see some diffuse plastic measure, is that the number of dislocation is also going to infinity. If not, you will only see Dirac deltas in the limit. Instead, you want to see something different. Also, you want to see that some dislocation collapse one over the other and create some diffuse plastic part, which is also what happens in the experiments. And the natural scaling is where the energy spent for a single one exactly competes with the number of dislocation you can produce. So you postulate that the admissible number of dislocation is again exactly of order absolute value of logarithms of epsilon, and this results in an energy of order square of the logarithms of epsilon. And so if you want to see some finite energy, because this one will be going to infinity, the natural idea is to divide your elastic functional with this factor 1 over 2. 2 is for mathematical reasons, no real meaning, actually any constant would do, to the logarithm of epsilon to the power 2. So this is the energy we will consider. It has a scaling. Now the scaling is exploding when epsilon is going to 0, and epsilon is also here. Epsilon is present in the fact that your domain has some holes. And so you want to fill these holes, but actually some new energy will appear. So this was the original idea, and the mathematical results, unfortunately, needed some more assumptions. So still I'm presenting previous work, but I guess I'm in time, and it is good also to introduce the problem. The unfortunate point is that this is the model you want to have, if you accept core radius, and as you will see in the second part where I present my and the others' contribution, we were trying to find an alternative to that. But still, your minimal model has to be furnished with additional conditions. And this is, from a mathematical point of view, one of the technicalities we have to take into account. So this is more for people interested into mathematics. There were some additional conditions that have to be considered, and it would be nice from a variational calculus point of view if one can get rid of them. So forget about the scaling, so you can put some assumptions. The point is that, okay, dislocations can homogenize, so you can have dislocations close to each other. But the condition you have to impose is that they are well separated. So that there is a minimal distance, which you call rho epsilon, this minimal distance is vanishing, so in the limit you can create some diffuse plastic pressure, but it's vanishing at some rate compared to your core radius epsilon. Clearly, this may have some physical motivation if you think of the macroscopic origin of your model. So in some sense, you want that there is some larger scala where dislocations see each other instead of the dislocation cores, which are way smaller, but it's a little bit not ideal because it would be good to get these conditions out. We were not able to. I will show you how they turn out to reappear in a different modeling as we will present. So for those interested, what a future plan may be. But let me stay to the present plan. So we have the energy, we have the scaling, we have the admissible configurations, we have to add some conditions to the admissible configuration. And this is this wealth separation assumption on the dislocation course. So there can be a lot of them. They can be of order 1 over logarithms of epsilon, but there must be some minimal distance between two dislocations, which is encoded by this additional parameter of epsilon, which is called hardcore radius. So if you accept this modeling, some 14 years ago, the first rigorous justification of a strain gradient plasticity model in the sense of gamma convergence appeared in this paper by Adriana Garroni, Giovanni Leoni, and Marcello Ponsiglione, which is called Gradient Theory for Plasticity via Homogenization of Discrete Dislocations. And I think that the title need not to be explained now. So it is clear what they did. They took this elastic model with the proper scaling and some conditions on the admissible configuration, and they took the limit as epsilon goes to 0. The first thing was to show that apart some rescaling and some subtraction of skew-symmetric affine motions, the dislocation density is converging to some bounded measure, accounting for plasticity, and that the scaled elastic strains are also converging to a limit strain beta. So this is the first one. Your variables, if the energy is bounded, have some compactness. I would like only to say something about these matrices S epsilon, and I think this will be the only place in the talk where I will mention them. It is natural to postulate that you have to subtract some skew-symmetric motion, because it is known that indeed the limit energy must only depend on the symmetric part of the limit strain beta. So you have no control on adding skew-symmetric elastic strains to your energy, and this is why you have to subtract them when passing to the limits. So in some sense, compactness, the existence of a limit is taking place in some quotient space where subtraction of skew-symmetric matrices is allowed. No real issue, but from the point of view of mathematics, this is very important because this requires some inequalities to be developed. So you take your energy competitors, possibly minimizers. What is sure is that they have bounded energy, and they are converging in some topology, some weak topology, but it is usually in variational calculus, to some limit configuration. So you have the limit plastic deformation density, which is a measure mu, and your limit elastic strain beta. And for those that are not very well into measure theory and variational calculus, it has maybe to be spent some words why you have to expect that actually plasticity is represented by measures instead than functions. And this is because of the nature of the energy itself from one side. This is a linear energy, and when you want to minimize, you cannot stay in 12.1. You have to go out and possibly incorporate measures. But also it is very well known that plastic deformation, also at a macroscopic level, can indeed concentrate on lines or hypersurfaces more in general. Since we are in L2, you have to imagine they can concentrate along curves. This is the phenomenon which is known under the name of shear bands. So this is not only mathematical abstraction, this is something that has to happen. That if you want a minimal model of this sort, which may be wrong for from a lot of point of view, but it is what people is currently using to understand the phenomenon, you have to accept that your elastic strain is an L2 function and you like it, while your plastic deformation is way uglier from the point of view of the structure because it may have some concentration, so it may be a surface measure, or it can possibly develop other kinds of singularities. So you cannot describe it by functions. You really need measures. And the second part of this result, which I'm recalling at the moment, is the derivation of the limit energy, which is what you expect. So now you have two variables, beta and mu. They are related by a differential constraint, so the curl of beta must be equal to mu. And the energy is made out of two parts, the elastic part and the plastic one, which is represented by a positively one homogeneous function. And you also have some asymptotic expression for it. So you know that you solve some problem on very small cells, you can have a characterization of this energy, which is called by now phi core. So this is what, since then there has been a lot of contributions, extension to nonlinear settings, different scalings of the energy, renormalize energy when one dislocation interacts with the others, but this was the starting point of a research program. On the other end, this was heavily based on this fact that this core-radius approach was used, and there were some attempts to remove this assumption. And we thought of a possibility based on a different modeling in elasticity, which is no more using the traditional strain gradients, but instead based on non-local interaction between elastic bonds. And when you want to do this, when you want to replace your local model with a non-local one, it is natural to use some notion of fractional gradients, which you may see as the action of some potential with some singularity on your configuration beta. And clearly there has been a lot of possible notion of gradients, and we use the one which, for the moment, seem to best suit the computations. But there is no, we are not sure if this is the best possible one, but it is an interesting possibility. So now I came to the second part, and I want to present this recent result of myself with my collaborators, which is also recently appeared on Mathematics Journal, which is the idea to recover the same model out of a different postulate. So no longer core-radius approach, but instead replace linear elasticity with fractional linear elasticity. And we show that in the parameter, in the limit where the non-locality parameter goes to 1, so we go back to a local model, we can recover the same energy or something similar, but of the same, but with different constants. And the motivation for this was really clear from the beginning. You have to introduce core-radius because you want too much from your linear strains. So you want that they lie in L2, and there cannot be no strain in L2 that accommodates both your energy and the curl constraint. If instead you use some models based on integral operators, there is a little gain in regularity, which allows you to not to cut out any region in your domain. So, as I told you, we need some integral operator to be defined. One of the most popular choices in mathematical literature is the risk potential. So, risk potential has a singularity at the origin. The order of the singularity depends on the space dimension. We are in R2, and so we have a singularity of order 2 minus alpha, which is an integrable singularity. Alpha is a very small parameter, which we, in the end, let to 0. And you need to put in front of your integral some constant to have everything converge in the limit. I will show you what I mean by that, and it is known how this constant must be and also how it scales. it scales like 1 over alpha in some sense. So you have 1 over gamma alpha here. You can think that you have some alpha in front of your operator, up to constants, which is 2 pi, but does not really matter. And actually, this is an approximation of the identity. So you want something non-local, which in the limit will give rise to something local. And so it is a natural idea that when alpha is going to 0, you have to recover the function you acted on. And this is a simple exercise. If you define this integral operator and you let the parameter alpha goes to 0, and this also explains the need for some constants, when you have a smooth enough function, say in CC, you recover pointwise your function in the limit as alpha is going to 0. Okay, this is the potential, but then you need a gradient. Accordingly, you can define a notion of fractional gradient. And as you may expect, how is a fractional gradient defined? You must replace the derivation with finite differences, and these finite differences are weighted by a risk potential. And there is also the multiplication for a unit vector, because you need to become a vector in the limit. So this is how you define the risk fractional gradient in the limit for smooth functions. And it is well known that this operator has some very nice properties, which were singled out in many recent contributions. As you see, I can single out some contribution from the last decade. There has been a lot of interest in this sort of operators. So for instance, if you calculate, you see, you define your fractional gradient at each point via a convolution operator. But when you instead integrate again on your space variable x and you take the L2 norm, what you obtain is a very well-known object, which is the Gallardo semi-norm in fractional Sobolev spaces, scaled by a suitable constant which can be explicitly computed. Also, this fractional gradient is the gradient of the risk transform of your test function phi. And the two operators commute. So you can calculate it. Also, you take your function phi, you apply the risk potential with order 1 minus s. Now 1 minus s is taking the place of our alpha. Then you apply the gradient. So you have something local plus something non-local. The result is in general non-local. And you can do it in whichever order you like, either first or second. Unfortunately, this notion of fractional gradient is not very well suited for mechanical problems on bounded domains. Why do we not like this? Because in some sense, you have something non-local, but this is highly non-local, in the sense that the behavior of a fractional gradient is depending also on what happens at very, very far away distances from your configuration. And this is sort of unrealistic. You do not want that. So the point was, you need a singularity at 0 in your convolution operator, and so far it's clear. But you do not see why you have to impose some conditions at infinity. Actually, in your mechanical problem, there is no infinity. You are on a finite horizon. And so in some recent contribution, the notion of fractional gradient defined via a risk transform was replaced by a milder one, which is better suited to mechanical problems, the so-called risk gradient with finite horizon. And the idea is very natural. So you cut something, you use a cutoff function. So you want something which is close to 1, close to your point x, where you calculate the gradient, and vanishes at some large distance which you can prescribe. So here you put some rho, and rho can be big, small, whatever you like. Clearly, if you let rho go to plus infinity, you recover the notion of risk gradient. So more or less, this is defined in the same way. And the point is, okay, now you have a better notion. You do not have to worry what happens at infinity, but do you have the same properties that a risk gradient has? Because if not, any attempt of using this approach for some variational problem is probably doomed to failure. And indeed, this is what happens. Some contribution of the very last 2 years showed that, for instance, you have a similar structure. So you can define your non-local gradient as the gradient of a convolution operator acting on test functions, so not really the risk potential, but something similar. And again, this construction commutes, this is good, and this construction, I always forget to introduce this slide, it was very useful to our purpose, the fact that indeed this operator is also an invertible one. So in the Schwarz space, as it happens, actually all of this theory is based on Fourier transform. So not only you can construct fractional gradients, but if you have smooth enough functions, you can invert the construction. As it happens, there is one where the inverse is also very well known, and it is the fractional Laplacian of order 1 minus s divided by 2. So I don't need this slide. I need this one. So now we are ready to introduce the model we studied. So the idea was to replace linear elasticity with fractional one. We have lattice directions fixed in order to have our Barker's vector, and we have a small unfortunate point also in our theory. So we have a finite horizon rho to be fixed in order to consider this. We would have liked that this finite horizon is small but fixed. Instead, we were not able. We needed that this finite horizon is also vanishing with alpha, and once it is vanishing, we have to postulate that it is vanishing on a certain rate. And this is sort of similar to what happens with corradius. So we need similar scalings, but now our leading parameter is no more the logarithms of epsilon, because there is no epsilon anymore. It is this fractional parameter alpha. And again, and this is also something we would like to work again on, we have to impose some condition of separation along the dislocation. If you accept that your finite horizon is vanishing, this is probably a natural one, because in some sense you are saying, okay, you have some non-local interaction. This non-local interaction is strongly localized. So we see what happens only at small distance from our point. Finite but small and going to zero. And so probably it is natural that, like the elastic energy is insensitive to what happens at a distance more than rho alpha, also dislocations are insensitive to each other, and so they must stay at this distance. The good point is now that we have admissible configurations. We do not need any corradius. We can formulate our differential constraint. So if we have a dislocation measure, we can have admissible strains whose curl actually agrees with this mu. How much time do I have still? Oh, okay. And we can introduce our model. So the model we introduce wants to generalize fractional elasticity. So if you have linear elasticity, you have strains, and it's natural to postulate that your energy is depending on fractional gradients of order 1 minus alpha and finite horizon rho alpha. In general, since our curl beta is different from zero, you cannot have an energy of this kind because your strains are no gradients anymore because of the presence of dislocation. And the natural idea, okay, but the fractional gradient is obtained via a risk transform. So for each beta, we put into the elastic energy the according risk transform with the finite horizon rho alpha. Then there are the usual assumptions on the elasticity tensor, but these are the real standard ones. So the difference with what was done before is there is no corradius. Corradius is replaced by use of risk type transforms on the linear elastic strain. And now your constraint can be formulated as a differential one, as it must be, instead of cutting out some pieces of your material and reformulating the constraint in an integral way. And so this energy is defined on the wall of your configuration. So it has a lot of similarity. It really resembles that one, but it's formulated in a different way. and it is different when rho stays finite. Instead, what is equal to the other case is the limit behavior that you can recover. And this can be done, in a sense, in the same way. First of all, you let your number of dislocations go to infinity, but you must know how much dislocations are admissible. So you have to calculate the contribution for a unit one. This you can do. So if you take a discrete dislocation measure, you can explicitly construct some competitors. You can calculate the associated energy. It is now a finite one, and it is of order 1 over alpha. If you have m dislocation, the energy associated to all of them is of order m divided by alpha. And so the natural assumption, as before, is having as much dislocation as the unit contribution of them. So m alpha equal up to a constant 1 over alpha. This is the so-called critical regime. Other regimes are possible, other descriptions are possible, but this was, in some sense, the most relevant case. And if you do this, you have to scale your energy, and the natural idea is to scale it by the square of alpha. Why did we put the 2 into the parentheses? I will explain in one slide. So these are the results we recovered. So again, under our assumption on the behavior with respect to one another of the horizon rho and of the fractional parameter alpha, we show that configurations with bounded energies are compact in the same spaces as it was before, possibly up to subtraction of some skew symmetric affine motion, which is part of the game and has to be accepted. And the limit result is of the same kind. So you recover a model of the same kind, and you cannot do better because this is what you want. If you want a minimal model, these are the assumptions that you need to take into account. So linear elastic energy on the limit beta, plastic energy on the plastic deformation measure mu, constraint curve beta equal to mu. The limit measure is the same features as it had before, so it is homogeneous of degree 1 as linear growth. And actually, with the choice of the parameter that we did, it can also be shown that we recover the same energy in the model by Garroni, Leoni, and Ponsiglione. While if you take different constants, you get some different multiple thereof. I think that they are always, in some sense, differing by a constant. But there was some choice that lets you recover the original model. And in some sense, and this is my real last slide, the point is that we can exactly characterize what happens in small balls when we consider our elastic energy. So when we try to recover a cell formula. So we take our elastic energy scaled by this parameter alpha on a very small ball B rho, and this problem actually cannot be explicitly solved, but we can show that, for instance, the distributional solution of this system of PDEs on the divergence and on the curl is close to be a minimizer up to some constant contribution, which is then vanishing the limit because of the parameter alpha. And once that we have that, all of our computation can indeed work. We need some uniform behavior, and this is why we introduced some scaling between rho and alpha, and if not, some extra contribution going to appear, and we have some explicit formula that is what we used in the end to calculate the limit energy. And this was the result, but as I told you, in the limit, we are going to get the same energy that was obtained before, but by means of an alternative approach that, in some sense, gives a link between fractional theories of linear elasticity and strain gradient plasticity theories. I guess I'm running out of time, but this was also the time to let the talk stop, and thank you for your attention.
Okay, first of all, many thanks to Francesco for your very clear and interesting talk. Are there questions or comments? Don't see any question. No. I want to wait for some question. Okay. Okay. If not, we thank again Francesco,
Thanks to you.
and we see for our next seminar. Good afternoon.